Here's a problem that involves phase change. So we have a 200 gram cube of ice at -5 degrees Celsius, and it's placed in a 50 degrees Celsius iron cup. The system reaches thermal equilibrium at 20 degrees Celsius. Determine the cup's mass. Now, our approach is the same as we've been doing with calorimetry, which is to say that, all right, sum of the Q's has to equal 0. In this case, I have two objects. I have ice and I have iron. And actually, let me rearrange this real quick. Let's put the iron first. Put the ice second. It doesn't matter the order, but I'm just anticipating how I want to talk about this, which is why I changed it. So Q iron, the cup itself, the cup isn't melting. The cup is just going to change temperature. So we already know our formula for that. That's going to be the mass of the iron. I need the specific heat of iron and the change in temperature for the iron. But let's talk about the ice. What is the ice doing? Well, the ice is at -5 degrees Celsius. So when it comes into contact with the iron, there's going to be heat exchange. It's going to go from the iron to the ice. And so consequently, the ice has to heat up. You might be tempted to say, oh, the ice is going to melt. But the ice won't melt until it's at 0 degrees Celsius. Right now, at least initially, it's at -5 degrees Celsius. So the first thing it has to do is heat up to 0 degrees Celsius. So I've got to do the mass of the ice. I got to do the specific heat of the ice. Okay. And I've got to do, and I'm just going to go ahead and put this in, it's the change in temperature of the ice. Well, the ice is going to start at -5 and go to 0. So it's 0 minus -5. Then it's going to melt. And melting requires heat to enter. That's why I've put a plus there, because remember, our formula for that, let me write it up here, is plus or minus ml. You have to choose the plus or the minus based on what phase change is occurring. Melting requires heat to enter, so I choose the plus. So this is the mass of the ice times L. Then what's going to happen after it melts? Well, now I've got this water that's at 0 degrees Celsius. This water needs to heat up to my thermal equilibrium temperature of 20 degrees Celsius. So it's still the mass of the ice, but now it's water. And I am running out of room here. Well, here, I'll just write this as delta T so I save space. This is going to be delta T for the water. I'll put a W there. Okay. Now, one thing about these calorimetry problems, sometimes the formulas get long. There's really no way around that. So now I'm going to start putting in all the values, now that I've written this out. The mass of iron, okay, we don't know that. We're looking for that. So I'm looking for the mass of iron. I know the specific heat of iron. I can look at my table, and if I do so, here's iron, 461. Change in temperature. It's going from 50 to 20, so that's going to be, oops, that's going to be 20 minus 50, okay. The ice, the mass of the ice, because my specific heats are in terms of kilograms, I'm using MKS units there with the specific heats, so my mass needs to be in kilograms. So the mass of the ice is going to be 0.2. Specific heat of ice, look that up as well. Let's see, where is that? 2095. 0 minus -5 is just +5. Okay. And then again, the mass of the ice, so that's 0.2. L is the latent heat. This is going to be the latent heat from going between ice and water. So that's right here. If I was going between steam and water, I would need this latent heat, but we're going between ice and water, so this is the latent heat I need. So that's 333,000. And that's joules per kilogram. Okay. and then 0.2, specific heat of ice, 4186. Temperature change, it's going from 0 to 20. So this is going to be 20 minus 0. That all equals 0. So that got a little messy there, but this is 4,186, the specific heat of water, which you can see right over here. And at this point, just go ahead and crunch the numbers. So that's going to be 461 times negative 30. So this is going to be negative 13,830 times the mass of iron plus this is 2,095 plus 66,600 plus 16,744. That all equals 0. Okay, so I'm solving for the mass of iron, so obviously I combine all these terms. I'm going to end up with the mass of iron. Let's see, when I add those all together, I get 85,439. I'm going to end up dividing that by 13,830. And so I'm going to get that the mass of the iron cup, 6.178 kilograms. And there you go. That's all there is to this. The crucial point is with these problems is back here in the beginning. Okay, this is our general approach, unless there's kinetic and potential energies involved. But if there's only heat exchange, this is our general approach. We identify how many objects we have. I had 2, the cup and the ice. And then I have to evaluate each individual Q. What's going on with the iron cup? Okay, it was only undergoing temperature change. What's going on with my ice? Well, it's undergoing a temperature change, but then it's going to melt, and then it's going to undergo another temperature change. So you've got that's part of the conceptual part, the physics part. You have to understand what's actually happening to identify that all these 3 terms were all part of Q ice.